Hi guys, welcome back. We are just proving here one theorem about the dual, so-called dual linear transformation. It is about given a bounded linear transformation between two normed linear spaces, you can uniquely define a bounded linear transformation between the corresponding dual spaces, however going the other way around, by a certain equality, which was the yellow star here. So let's quickly look at it one more time. It is this one here. Maybe I will erase this yellow stuff and this yellow stuff. This is the defining property of the dual. Okay, we have proven a few things. We have proven that it is well defined by this yellow box, that it is an isometry, and we're almost done with the linearity because we did this little computation up here. So if you look at the green underlined pieces, then from that I would like to conclude, well, because this here after all would be the alpha A plus beta B transposed acting on F and then evaluated at X. If the dual is uniquely defined by the yellow property star, then indeed I can immediately jump on this one, which asserts the linearity of the map, okay, sending A to its dual. Yeah, but how do I prove this now? So how do I prove that yellow stars uniquely defines the dual? Well, that's easy. So hence this showing it as a dual is linear provided the dual is uniquely defined by yellow star, right? So, but this is easy to see, but this is easy to see for if you have two guys, a one dual and a two dual are both dual operators, so linear transformations to the given A, and both satisfy yellow star for the given A, then, naja, you want to show that something is equal to 0, take the norm and show that the norm is equal to 0. So let's do this. Let's look at the operator norm of the difference of these two dual guys, and then going through the same double optimization that I did earlier, right? So outside there is a supremum over linear functionals, and inside there's a supremum over points in the vector space. Okay, and it was a1 dual minus a2 dual f of x, like this. And now you use what you already showed up there, namely by pointwise definition. This is going to be a1 f of x minus a2 f of x. Okay, but now by assumption the a1 and the a2 with the t on top, they are both dual to the same a. So that means the first one is f of ax and the second one is also f ax by the yellow star, right? So but then here you optimize over a difference of the same vectors, and that difference is 0, so that, well, extreme value here is also 0, right? So and that means in particular that these two duals have to be the same. In short, the dual linear transformation is uniquely defined by the equation with the yellow star on the previous slide. All right, so let's write it down. A1 dual is equal to A2 dual. It has uniqueness is established, and thus also this map, of course, well defined, because to one input it assigns one output, right? All right, and that concludes the proof of this first theorem. All right, so the dual, of course, on the surface it looks quite technical, but the dual transformation is extremely useful because it allows you to get information about the dual space of nonlinear spaces, and then in particular about the dual space of Banach spaces. So we have to keep it in mind, and since it is so important, I will summarize a few of its properties. 3 of those. One we already proved right now, but nevertheless it's a good thing to have them all summarized in one theorem. And the other 2 outstanding properties you will prove in the exercises. They're very simple to prove. You just play around with that yellow start equation, the defining equation, and you'll find it. Okay, so let's state it first. So let A and B be 2 bounded linear transformations. Be 2 bounded linear transformations between 3 normed linear spaces, x, y, and z. Okay, and z. All right, and let the dual of A and the dual of B be given. And those guys exist because of the previous theorem. Okay, denote their duals. Then, property number 1 that we already proved, the map that assigns to each given bounded linear transformation A its dual is well defined, and it is a linear isometry. See last theorem. It was part of it. Number 2, well, think about linear algebra and 2 matrices. So I said earlier some people call, including myself, every now and then, but I try to avoid it as good as I can. Some people call this transpose because it has similarities to the matrix transpose. And if you have 2 matrices, B and A, and you form their compositions of the matrix product, and you look at the transpose, then you can compute that matrix product as the product of the individual transposed matrices. However, the order gets flipped. Now, turns out here the same is true for these linear transformations, and that's one of the properties that you will show in the exercises. Maybe let me move that T here. Okay, so it satisfies the exact same property. But these are, of course, here maps on infinite dimensional spaces, not matrices. Okay, then the dual of A is injective, provided A is surjective. That is really easy to see if you just look at the yellow star. Moreover, if A is invertible, remember what that means. So it's bijective and the inverse is bounded. Then so is the dual. Okay. All right. And we have well, the formula that you know from the matrices. If you take a matrix as inverse and then the transpose thereof, then taking the inverse and the transposition, these 2 operations, they commute, and the same is here. So the dual of the inverse is the inverse of the dual. Okay, so that is true. These 2 properties, 2 and 3, these you will do in the exercises. Now you might be tempted to think, okay, let's push this analogy with the matrices a bit further. So if I have a matrix and I take its transposed and then I do again the transposed, then I swap rows and columns and swap them back, then it is the same, right? In infinite dimensions, this is not true. Absolutely not in general. Okay, in that sense, they greatly differ from just taking matrix transpose things, right? So this is in general not true. So I will erase it. Okay, good. All right, so now moving ahead, I already said the comment about some people call it Banach space adjoint or transposed, and the Banach space adjoint is justifiable because there will be later on the Hilbert space adjoint, and these properties, these three here, that is something you will recognize again when we do the Hilbert space adjoint. Nevertheless, as I already said it before, and I will say it again now, and I will say it again later when we discuss the Hilbert space adjoint, these objects, Banach space adjoint or the dual here and later on the Hilbert space adjoint, they are different maps. Okay, good. Now, having now done this, so let's push the wagon further. So if you have a dual space, then a consequence of the Hahn-Banach theorem says that then this guy is really big. There's lots of linear functionals on a given normed linear space. So now this begs the question to study the dual then of the dual space, right? Because the dual space itself is big, so what about linear functionals that act on linear functionals? And that brings you to the second dual, and that will be part of this definition. So let X be a NLS, the dual space, so X double star. So these are the linear functionals that act on linear functionals on X. Okay, so of the dual space, X star is called, okay, there's many names for the same thing, is called the second dual. That's I think what I usually use, bidual, or the double dual. Yeah, I think bidual and double dual, that's what I usually use. I don't think I ever use second dual of X. Okay, so that is it. And then of course once you have the bidual or the second dual, then you can put another star, go to the third, fourth, so on and so forth, and all of this will play a role. Okay, but okay, let's first understand a little bit the bidual, and then we will see if we really need the the 35th dual or not. All right, so given X in X, the rule, so I have to define a linear functional that acts on linear functionals on X, and this will be the standard notation J sub X acts on a linear functional, and it should spit out a scalar, and the not a scalar, a scalar, an element of the underlying field. And the easiest way I can do it is this. I just set it equal to f of x, a point evaluation of f at the given vector x. Then this defines an element j sub x in the bidual, right? Because it takes a linear functional, so an element of the dual space, and it assigns to it a scalar, precisely by this rule. Okay. Having this, we thus have a, probably D is better, canonical map, which is J, which goes from X to the bidual, and it assigns to a given vector X that map J sub small x. Okay, so in other words, the J of X is just capital J acting on X is just small j with subscript X. Okay, this is the thing. That's a very, very important thing. Probably one of the most important maps that gets a name in this entire model. The canonical map that maps you from a given nonlinear space to its bidual. Okay, It's so important that it gets its own theorem, and we will summarize some of its properties in that theorem. Okay, so let X first be a general normed linear space. Then, well, some facts up front. That guy is really a bounded linear transformation, that capital J. All right, and moreover, it's injective, better even, it is an isometry. So it preserves the norm. That will be again a consequence of Hahn-Banach. In particular, this is what I said first, J is injective. And provided X is a Banach space, the range of J is a closed subspace. Remember, ranges in general are not closed subspaces. Kernels are of bounded linear transformation, but the range is in general not a closed subspace. But here, for the canonical map, provided the given NLS is complete, it is a closed subspace. That makes it really special, because that doesn't happen often. There will be later on in chapter 4 the projections. They have a similar property that their range is always closed subspace, but in general that's of course not true. Alright, so now let's check this. So first that it's a linear map, then that it is bounded, then the isometry, and then the range being closed subspace. Alright. So by, oh yeah, I need another star. So the defining equation for that little j is, since we already had one yellow star, let's use two yellow stars, is this guy here. So we will exploit this now all the time. Very much like the definition of the dual. We also exploited that yellow star a lot. So let's do this. So by yellow double star, so j of alpha x plus beta y acting on f, now I use the double star, is what? So remember how this acts. This takes f and then evaluates at the vector which is written there in the subscript. So alpha x plus beta y. Now f is linear, so this equation here, this will hold for all x, y in x, for all linear functionals, and for all scalars alpha, beta. For all x star, right? So then this is alpha f of x plus beta f of y. Oh my, I'm running out of space. And like this. And now you use that, well, this is your jx of f, and this is your jy of f, and then you use the pointwise definition. So you have alpha jx plus beta jy acting on f. Right. Alright, so now if you read this green underlined stuff being equal to that green underlined stuff, then this is precisely the linearity of capital J as written up there, because capital J of x is J sub x, right? So what I proved now is, from this green stuff, that J of alpha x plus beta y is equal to alpha J of x plus beta jy, and that's linearity of capital J. Alright, good. So Jx to the bidual is linear. Next they will show it is bounded, and since we'll prove more. We will already get in the direction of the isometry. So what's the operator norm of J? So it is supremum of x in x. Well, let's go over the boundary of the unit ball. X equal to 1, j of x. But now careful here. This norm inside the supremum, this is an operator norm because j assigns a vector to an element in the bidual, right? So, but nevertheless, let's first use the definition of the small j. So this is just small j x. And now small j of x is by double star. Oh no, I'm not using the double star yet. I'm going slowly. So this is an operator norm inside. So this is the supremum over linear functionals on x, and then jx of f, right? Because it's an element in the bidual. All right, so you have this, and now you can use the yellow star, double yellow star, that is, right? This here is f of x, and then if you have it like this, then the same old trick that we have used multiple times is equal to that, and then you optimize both f and x over the boundary of the unit balls in the respective spaces, so they are both at most 1. So that whole thing here is at most 1. All right, so indeed J is a bounded linear transformation between these two spaces. Okay, excellent. Moving ahead, we now prove the isometry, and then finally that the range is closed if X is complete. So from the last estimate, which is that the operator norm of J is at most equal to 1, we get at once that J of X is less than or equal to the norm of X in X space, right? That this is just because, this is supremum of J of X over X, right? And then the supremum, of course, is an upper bound. So then you get it, you erase the supremum, and then you have an inequality, and you multiply the X to the other side, and you have what I write there. Okay, so you have this, all right, and on the other hand, by Hahn-Banach, given x naught in X, there exists linear functional G on X, so that G of x naught, this was, however you count, the first or the second corollary to Hahn-Banach, the first being, again, paraphrasing Hahn-Banach in terms of norms. Then this was the first real corollary asserting that dual spaces are sufficiently large. There's plenty of linear functionals. And that was saying that given a point, you can find linear functional that is equal to the norm of this point at the point. And the operator norm of the linear function is equal to 1. All right. So if you now look at the norm of x like this, then this is equal to gx naught. Yeah, but remember the linear functional is a norm equal to 1, so I can artificially write it here on the left. Okay, and by double star, this is precisely equal to gx naught of jx naught of g. All right. In turn, jx naught, which is the supremum over that thing again, jx naught f, is at most equal to jx naught, is at least equal to jx naught evaluated at g, because g is a linear function with norm 1. So, and then this guy is equal to, well, x naught. Yeah, I actually don't understand why I artificially introduced here that g up there. Doesn't seem to play a role at all. Because this is all good. Yeah, that's the only thing I need. It's not true, but it's not wrong, but it seems unnecessary. Okay, so you have this, and now if you, of course, read this and that, since this works for any x naught, you get the converse inequality to this guy up there. So altogether, there has to be equality between these two norms. Altogether, j of x is equal to, for all x and x, meaning j l x x star is an isometry. Okay, nice. Good. Doesn't particularly injective, because isometries are always injective. Okay, now looking at the time, since the last video went a little bit longer than I wanted it to, maybe I will stop here. So we still need to prove that the range is closed if X is complete, but that is not hard. And then remember the last result in the previous section was that if you have a Banach space and the dual space is separable, then the space itself has to be separable. And I said the other way around is not wrong. It's not true. It's wrong. It only works for a special class of Banach spaces, and that special class will be introduced right after we have finished the proof of this current result. But this I will then do in the next video. Okay, see you then.